In this video, we're deriving the formulas for taking derivatives of the sine and cosine functions. And we're going to start this out with the geometric motivation for these formulas, and then we'll get into the proofs of the derivative formulas by using the limit definition of the derivative. So in our animation, we're viewing the sine function on the left and the cosine function on the right, and we can see the calculation of the slope of the tangent line to each of these curves as we move from left to right. Below each of our curves, we plot the derivative function, and that's the function where the y value is the slope value of the original curve. So as these derivative functions are constructed point by point, we start to recognize some familiar functions. On the left side of our screen, the derivative of the sine function appears to be the cosine function. And on the right side of our screen, the derivative of the cosine function appears to be the negative of the sine function. That's just the sine function reflected about the x-axis with that factor of -1 sitting out in front. So that's not a proof that the derivative of the sine is cosine and the derivative of the cosine is negative sine, but it's pretty compelling evidence. So to get into the proofs, we actually need to remember two important limits that we derived in an earlier video, and I'll post a link to that video up at the top. First, we have the limit of sine x over x as x goes to 0, and that's equal to 1. Note that this limit isn't obvious because sine x and x are both approaching 0 in the limit. In other words, it's an indeterminate form of the 0 over 0 variety. And the derivation of this limit actually required a pretty tricky geometric construction. In our second important limit, we have the limit of 1 minus cosine x over x as x goes to 0, and that turns out to be 0. Again, this is an indeterminate form because cosine x goes to 1 in the small x limit. So this limit is going to the indeterminate form 0 over 0 again, and this one was actually proved by using some trig identities on the first limit. So these are the two important limits we need to remember in order to apply the limit definition of the derivative and prove the derivative formulas for the sine and cosine functions. So here's the main project of the video. We need to symbolically compute the derivative of the sine function and the derivative of the cosine function. And for this, we need the limit definition of the derivative. And I'll post a link at the top to where this limit definition of derivative was first derived. So when we apply the limit definition to the sine function, I get the limit as h goes to 0 of sine evaluated at x plus h minus the sine function evaluated at x itself, and that whole thing divided by h. To make progress on this limit, we see a sine of a sum of two angles. So naturally, we're going to try applying the formula for the sine of a sum of two angles to this. So the way that formula works is that we take the sine of the first angle, so sine of x, times the cosine of the second angle, and that's the cosine of h. And then we add to that the cosine of the first angle, so cosine of x, sine of the second angle, so sine of h. And then the minus sine x is a spectator. Now that whole expression is divided by h. So now I want to point out that x is a constant with respect to this h limit. So we're thinking of sine x and cosine x as constants up there in the numerator. I notice in my middle term, I have a sine h. So I can end up with something that looks like sine h over h in the small h limit. And this is encouraging because that's one of the special limits from the previous slide. Now in our other terms, the first and third terms, I have a sine x as a common factor there. And remember, that's a constant with respect to the h limit. And if I factor that out, I end up with a cosine h minus 1. Well, that's really closely related to 1 minus cosine h. In other words, we're seeing that second special limit. So we have some rearranging and factoring to do here. And for our first term, I'm going to handle those sine x containing terms up there in the numerator. If I factor a sine x out of that, I get cosine h minus 1. And then my remaining term is going to be a cosine x times the sine of h. Now at the same time, if I have a sum or difference of two things in the numerator divided by this h, I can just split that into two separate fractions. All right, now again, the whole goal here was to recognize those two special limits. One of them was sine h over h, and I see that occurring in my second piece. And one of those was 1 minus cosine h over h. And what I notice is the order is wrong on that difference, but you can always reverse the order of a difference by factoring out a -1. So what I'm going to do in the next step, remembering that sine x and cosine x are just constants, is I'm going to split this into a limit of the first term plus the limit of the second term. And I'm going to factor a negative sine x out of the first term. So we're getting the sine x out of there because it's a constant, but we're pulling a negative 1 out also because we want to reverse the order of that difference. So in our first term, we've highlighted one of our special limits. And the second term here is a little bit simpler. I can just pull out the cosine x, and then I'm left with the limit as h goes to 0 of sine h over h, and that's our other special limit. So remembering the values of these special limits, the limit as h goes to 0 of 1 minus cosine h all divided by h, that turned out to be 0. So that whole first piece of this expression is gone. And then the limit of sine h over h as h goes to 0, that turned out to be 1. So the only survivor of this limiting process now is cosine of x. And we have our proof that the derivative of the sine function is just the cosine function. So now we're going to do a similar thing with the cosine function. Again, we apply the limit definition of the derivative. So we find that the derivative of the cosine function is the limit as h goes to 0 of cosine of x plus h minus cosine of x all divided by h. And this time we need to remember the formula for the cosine of a sum of two angles. So the way that works is we take the cosine of the first, cosine of the second. So cosine x times cosine h minus sine of the first, sine of the second. So sine x minus sine h. And then this negative cosine x is a spectator. And that whole thing is divided by h. Now again, what we're trying to do is isolate these familiar special limits, sine h over h and 1 minus cosine h over h. And I can see in my cosine x terms, that's the first and third term, if I factor the cosine x out of those, I get a cosine h minus 1. And my remaining piece is going to be a sine x times sine h. And again, at this point, I'm going to go ahead and split this into two separate fractions. So the first one is cosine x times the quantity cosine h minus 1 all divided by h. And then I have minus sine x sine h all divided by h. Now we're going to split this into two different limits and do some factoring. I'm going to pull a negative cosine x out of the first one. Again, pulling out that factor of negative 1 allows me to reverse the direction of the difference. And now I have exactly one of my special limits, 1 minus cosine h over h. And then in my second term, I have a minus sine x times the limit as h goes to 0 of sine h over h. And that's our second special limit. So that cosine limit, 1 minus cosine h over h, vanishes, so that whole term is gone. And then the sine limit, sine h over h, that goes to 1. And the only survivor of this process is negative sine x. So the derivative of cosine x is the negative of the sine function. So now that we have these nice algebraic formulas for the derivative of the sine and cosine functions, we can use these to quickly compute derivatives of more complicated functions involving sines and cosines. So in our next video, the goal is to compute derivatives of the tangent, cotangent, secant, and cosecant functions. And because these are defined as fractions involving sine and cosine, we'll be able to find these derivatives by combining our new sine and cosine formulas with the quotient rule. I'll post a link to that video at the upper left, and I'll see you there.